Ideas are fun. Combinations of ideas, even better. It's exciting gathering a bunch of these precious creatures that have never seen each other before into a new design, like a weird engineering menagerie. But you have to be careful because sometimes some ideas just aren't meant to be mingling with others, even when they are from the same country. So tread cautiously, because you never know when a good idea can go bad. Welcome back to Inheritance Machining. Quick refresh. I'm in the middle of making this big fancy radius turning tool for the lathe, and based on the number of confused comments I got in my last video, I didn't do a good job explaining what that actually means. So, this is a lathe. Lathes make round parts, and sometimes it's nice to add round corners to your round parts. Only trouble is, this cutter can only cut one size, so you need a whole brigade of internal and external radius tools, which isn't cool. What is cool is a tool that can cut any size radius in any direction. Which brings me to this beefy piece of kit. Behind this curvaceous exterior are three important components: a pair of crankshafts that can be shifted along a dovetail slide, and a tool holder that rides on those cranks. The combination of which takes a cutting tool through a circular path that can make round corners, among other things. And to set the radius, we just offset the spindles on those dovetails. Pretty clever, right? I thought so too, until I was informed my design already exists. Naturally, some Germans beat me to it, by a near margin of several decades. That point aside, I'm still eager to get this thing lathe ready, and that brings me to the subject of this video. I need to synchronize the two spindles, because if I don't, they lock up tighter than a gnat's ass. There should be something that keeps them both rotating in the same direction and at the same speed, particularly when they have to go over center. Chains, cables, belts, and gears, which are what the Germans used, would all do this, and I actually made a whole list of pros and cons of each approach. But then one glorious individual in the comments suggested a needlessly weird mechanism I had never heard of before. They had me at needlessly weird. She suggested the NSU Ultramax camshaft drive mechanism. It's basically a linkage from a 1950s motorcycle engine that synchronizes the rotation between the crankshaft and camshaft. In other words, exactly what I need. And guess who invented it? Ding ding dong, you guessed it. Germans. But after printing one up to play around with, the pros and cons list went right in the trash, because this thing is too effing cool. There are a pair of spindles with eccentric lobes that are out of phase 90 degrees from one another, linked by a pair of connecting arms. The 90-degree phase difference being the key part of this, because when one connecting arm is in the over-center position where it would bind up, the other one can still drive it past that point. It's a super simple and clever design, but as I suspect, not very simple to make. I'm pretty well rested and ready to rock though, thanks to our sponsor, Helix Sleep. They make mattresses that, to put it bluntly, kick ass. But, in a good way. I don't know about you, but I take my sleep seriously. Everything has to be just right, because you just can't compromise on where you spend a third of your living and 100% of your sleeping hours. Helix agrees. That's why they developed a lineup of 20 different mattresses to suit every sleeping requirement. From sprawlers to huddlers, belly up or belly down like me. That's why Helix has their online sleep quiz to target your specific sleep needs. They take into account things like you and your sleeping partner's sleeping positions, weights, and where you guys hurt most in the morning. Then recommend the best mattress from their lineup that suits you and deliver it in a compact box, so it's just a matter of open and sleep. And if you're not feeling better rested after 30 days, they'll take it back. Helix knows mattresses are a significant investment, and maybe you just bought one, but it ended up sucking. Or you just don't want to spend a bunch of money on the guest bed that only gets used when you forget certain holidays. Well, Helix now offers a line of mattress toppers, so you can take that old college bed and make those lonely nights not so bad. Seriously, this topper pad is great. So head over to helixsleep.com/inheritance machining to take advantage of their 4th of July sale. Using my exclusive link will get you a special 27% off site-wide. Try Helix Sleep and get the sleep solution just for you. Okay, let's get into it. I'm going to start with a pair of connecting arms for no good reason other than they'll be fun to make, because they're bronze. I picked this metal for two very important reasons. First, bronze is slippery. These two arms will be rotating on hubs as well as sliding against one another, so slippery is good. The second and possibly more important reason is bronze looks cool. I planned ahead on this one and bought oversized 1/4 inch thick bar stock so I could put a nice finish on here, but I guess McMaster had a different definition of extra thickness. So we've got a little bit more than expected to take off here to square these up. Both of these connecting arms are going to end up being identical, so might as well try and cheat a little and do them at the same time. It's generally not a good idea to machine parts stacked like this though. The top one can come a little bit loose when the vise is tightened, but a little bit of malleable aluminum should eat up that difference and keep everything snug as a hug from a thug. Yeah, don't listen to me. We'll do these individually. There are 4 pilot holes that will end up helping with some milling later, but the key focus for now are the larger holes on either end, which are bigger than my biggest hole poker, so we'll cue up a boring interlude. The mechanism I'm plagiarizing had to be pretty robust being inside the hot and shaky environment of an engine. My tool will never see anything like that, but that doesn't mean it doesn't need special attention. And there are 3 critical points to hit. First, and by far the most important, is the spacing between these 2 holes. It needs to be dead nuts the same as the spindle spacing on the assembly, otherwise we'll have another sphincteral situation. Second are the diameters, but we have some wiggle room here since I haven't made those mating parts yet. And the third most important thing, of course, the chamfers. Okay, let's start bringing some shape to this thing. Those 4 holes from before are the corners of the neck down section. In engines, this narrowing of connecting rod between the larger ends reduces weight and vibration, but my tool isn't going to be rotating anywhere near those kinds of speeds, so this is just to make it look cool. And that wouldn't be complete without some of these. Can't forget the other side. I have to relocate the part though, so the coaxial indicator takes care of that, and I can miter away. Oh, the lengths we go to for a nice chamfer. So far so good. If you're curious how the second one was made, then rewind to about here. Otherwise, let's round these out. I've got a couple ways to do this, but it's been a while since this old friend has made an appearance, so let's use the rotary fixture. With this, I can clamp the part to the table and sweep it around to cut all these silly corners off, but that's only going to work if this part is centered on the table, so let's side project. Alright, now I know it's centered. So I'll offset the correct amount, run the fixture against its hard stop, and use a gauge pin to position the part at that starting angle, clamping it down with some buffer material underneath. Then to set the stopping point, I'll sweep around locating the other side, and place another hard stop here. This gives fixed beginning and end points that, if I did everything correctly, should be the same for all 4 ends. Of course, there need to be chamfers, and of course they need to blend nicely. So setting the depth right in the existing chamfered section makes this a cinch. And after the first end, the rest are all just located with the gauge pin. For this last part, I'm not going to need the stops at all because I need to go full circle. I'm going to do a smart and relieve the face of the connecting arms a bit like this so they only rub against each other right near their bores. I think this will help with any potential binding or unnecessary friction between the pair of connecting arms.
Oh, well that was stupid.
Okay, maybe not so smart after all. All that effort to meticulously chamfer the entire perimeter, and I cut it right off. Genius. But we'll come back to that, don't worry. Okay, a bunch of time later and they're finished. And I think they turned out great, but they're only one part of the equation. They won't do anything to keep these spindles synchronized without the cam lobes, so take a wild guess what we're going to make next. To start, these are pretty simple, just some round donuts. The end part looks simple too, a pair of eccentric lobes around a central bore and out of phase from one another 90 degrees. How hard could they be? Well, when you really think about it, pretty hard. There's not a good way to hold on to something like this. Furthermore, while the 90-degree phase angle itself isn't deathly critical, it could be anywhere in that ballpark, what is deathly critical is that I need to make them both exactly the same. I have a plan for this though. We'll get to that in a minute. It's hard to see, but the parting sides of these discs are a little bit wonky, so I need to clean that up. I could fiddle around with this on the lathe in the four-jaw chuck, but I've got a hankering for some aluminum oxide, so let's use the surface grinder. I placed the parts face down, and you can see just how out of flat the opposite parted side really is. There's kind of a hump in the middle that I'm grinding away. Starting on this side also guarantees that the faces end up perpendicular to the central bore, which may not make a whole hell of a lot of difference, but might as well shoot for accuracy when possible. And while we're here, I'll do both sides, for samesies. Alright, with the blanks ready, let's get to the good stuff. I could spend 10 minutes explaining all the ways I decided not to make these, but that would be highly pedantic, even for me. So let's just stick with how I am. It all begins with this hole. It's kind of the central point to all the stuff to come because everything mirrors around this feature. That statement will make sense soon. For now, this hole gets a pin that has a couple purposes. The first is to locate the disc in a fixture, so let's make that fixture. This fixture is actually two parts. The first one gets a little nubbins that is a perfect fit for the bore on our blanks. After parting this off and cleaning up the other side, this gets popped in the mill and located with a coax before drilling two holes. A simple center drill that happens to be the central axis of one of the offset cam lobes, and a through reamed hole that, if I did this correctly, should perfectly locate on the pinned blank. The second piece of this fixture is the same, except different. One end gets turned down to a size I can fit in a collet chuck, where it can then be flipped around and nubbinsified like the first. But there's an important reason for this difference. After mounting this piece of the fixture in a collet block and then locating and reaming a pinned hole here as well, I'm going to leave it in this collet block and head back over to the lathe. You see, now that I know the angular position of this hole relative to the 90-degree faces of the collet block, I can put this whole thing in the four-jaw chuck to set the cam lobe offsets I need while maintaining the correct angle to the pinhole, indicating it centered first, then shifting the whole thing with two opposing jaws to get the offset. And here's where it all comes together, because if I did this all right, the pin blank should slide on here like this, then the first half of the fixture, and then the tailstock. Perfect. Now I have a nice offsetting fixture for turning the lobes. The only question is, can we do it? While mesmerizing the watch, it's pretty slow going. I also realize at this point that the tailstock side of the fixture kind of gets in the way, but cutting right through it is of no consequence. So after facing the exposed side and getting the diameter spot on, one of the connecting arm slides on here splendiferously. It seems this fixture works exactly as intended, but here's where it gets even cooler, because to cut the other lobe, I can just flip this around. Remember how I said this part is mirrored about its pin? Well, because that pin is 45 degrees off axis from the square collet block faces, flipping it around means that I can cut the second lobe exactly 90 degrees out of phase from the first. I will mention though that even with this, there's still the chance it's not exactly 90 degrees. There will be some error, albeit small, in how the four-jaw chuck grabbed the square collet block. But I'll reiterate from before, the angle isn't important. I just need both of my parts to be identical. So if I just don't take anything off the lathe, I should be golden. After some sneaky chamfering, we're done. At least enough to see if this maybe, possibly, hopefully is going to work. I'm feeling a distinct lack of the warm and fuzzies. The pieces spin freely when the joints are by themselves, but when it's all together, not a chance. I'm guessing, or more accurately hoping, the cam lobes are just cocking off axis a little and binding things up. If I go ahead and get these mounted on the main assembly spindles though, that should keep things straight. And then we should see that awesome movement we've worked so hard to achieve, but of course not without more work. If you've been around here from the beginning of this project, you're probably laughing because this makes the second time I've mounted these spindles for modifications, but that's just how it is. When you don't know exactly where you're going, you can't possibly know exactly how to get there. I'll figure out the threads I unceremoniously turn to chips later. Right now, I just need to know if this thing is going to work. So I need a hole for the cam lobe pin in this face. As you might have guessed, it needs to be at the right angle, in this case 45 degrees from the dovetail axis on the other side. The best way to do that is to grab it by the dovetail axis on the other side, with the aid of some pins. From here, it's going to look pretty familiar, though I don't have a long enough center drill to reach down to this face, so hopefully this engraving bit works. Buddah Baybay. With the second one whipped up, I think you know what we're going to do from here. Look at that. Freaking awesome, right? The magically mesmerizing mechanical motion I've so longed to see. Incredible. But looks can be deceiving. The whole point of this linkage is so that when I turn one spindle, it also turns the other, keeping them synchronized. But that doesn't seem to work for this, like, at all. It will only spin if I turn both by hand. It goes all the way around, so I don't think there's a dimension wrong anywhere or this would just bind up. Heck, the 3D printed model is all loosey-goosey and it still works. So maybe it's a friction thing? Extra torque certainly doesn't overcome it, despite it not being hard at all to turn by hand when I do both. I am seeing some backlash though. It's able to wiggle even though it's not rotating. All the mating clearances are pretty small, but so is the cam offset distance. The combination of these two mean there's some small angular error. This will definitely affect the circular accuracy and the ability of this tool to cut truly round corners when it's done, which is a bummer, but it also tells me something else. The short cam offset just isn't enough leverage to get the job done. Like, if the cam offsets were way out here, they'd probably have no trouble at all, at least in proportion to the amount of friction in my design. The only things I can think to do about this are to either load this thing up with bearings, which would be a complete redesign, loosen up the tolerances, which throws accuracy out the window, or create a continuously circulating lubrication system like you would see in NSU's motorcycle engines, which sounds messy. So I think this is just one for the books, or rather box. There's also the chance that I'm completely missing something obvious, or this was only ever going to work if I was a German YouTube channel. Let me know what you think in the comments. Otherwise, I'm going to assume that there's a good reason this technology hasn't been used in 50 years, and why NSU secretly stands for not something you want to mess with. As always, thanks for watching, and see you next time.